Now that we've talked about the formal definition of a partition, we're going to relate it to the equivalence relations we've been talking about over the last couple days. And so I want to start by just reminding you of one of the equivalence relations we've talked about before and some of the structure we saw with that equivalence relation, because it will make it easier to understand the statement of the lemma we're about to prove. And so we talked about mod 3 on the set 1, 2, 3, 4, 5, 6, 7, 8 before. Now I'm going to talk about it on all of the integers. And we saw that you could divide up the set, in this case z, into different clumps depending on the relation. And so what I mean by that is that we could write out all of the things that end up being equal to 0 mod 3. And so that'd be 0 and then 3, 6, 9 and so on upwards. And then if I subtract 3's, I'll get the other negatives as well. And so I could do the same thing with the things that are equal to 1 mod 3 if I'm viewing mod as an operation. And so that'll be 1, 4, 7, 10, and then again subtracting off 3's to get the other side. And then we would just have one more set right here, which would be all the things that are equal to 2 mod 3. All right, and so one of the things that's really special about equivalence relations is that it turns out that if you take any two numbers that are on the same line here, so in the same set, then they will end up being related to each other. And so, for example, if I take this 6 and this minus 9, because they're on the same line as each other, I know that they have to be equivalent mod 3, or in other words, I'm just saying the remainder for both of them is 0 mod 3. And on the other hand, I could do the same thing for either of the other two lines and I'd get things that are related, but I can never have things between lines that are related. And so what we'll end up doing is calling each one of these lines an equivalence class, because everything in the same line is related to each other, so they're all equivalent. And then we can say that this set z, so all of the integers, were partitioned into 3 different equivalence classes. One of them which is 0 mod 3, one of them which is 1 mod 3, and one of them which is 2 mod 3. And so that is actually a very special property. In general, relations do not divide up your set into nice chunks like this. But for an equivalence relation, we will prove that it always divides up your set into these nice bands where everything's related within a band and nothing's related between different bands. And so in order to do this, we're going to add a little bit of notation. And so we're going to want a way of referencing each one of these equivalence classes. And the way we're going to do it is by writing e sub 0, e sub 1, and e sub 2. And so by definition, we'll let, for example, e sub 2 be the set of all of the integers, so the x's and z, such that x mod, or I should say, x is related to 2. And so the reason why I want to write related instead of mod here is because this is a general thing that we could write for any relation. So e sub 2 is always going to be the set of objects in your original set that are related to the number 2. And so now each one of these, E0, E1, and E2, makes sense according to this definition. It is the case that this notation is flexible in the sense that we could have written these sets in more than one way. And so it turns out that this top line is actually the same as e sub 3 or e sub minus 6, because the things that are related to 0 are exactly the same for this relation as the things that are related to 3 or the things that are related to minus 6. That wouldn't always be true for general relations, but in this case it is. And so now our goal is going to be to show more abstractly that if we have any relation, it always partitions your set into distinct equivalence classes. And so let's look at the statement of this lemma. And so it says any equivalence relation partitions your set X into these equivalence classes. And then also it says that for any two elements in your set, they're related to each other if and only if they're in the same equivalence class. And so again, going back to this example, it's just saying Z is divided into chunks, E0, E1, and E2, and everything within each of these chunks is related, and nothing between different chunks is related. All right, now we have to figure out how we could prove this sort of abstract sounding thing. And because there are multiple parts to the statement, the proof is going to have multiple parts as well. And so the first thing we're going to want to show is that X is partitioned into equivalence classes. And so we saw before that the definition of partition has several different parts to it. The first thing we're going to need to show is that for all x in x, x is in some equivalence class. And then after that, we're going to want to show that for all x in x, x is in at most one equivalence class. And so these two things combined really have that idea of a partition, where a partition is just dividing your original set, where each part in your original set goes into exactly one clump in the partition. And so one of these parts of the proof is going to be easier than the other. So if we want to show that x is in some equivalence class, that's really easy to do. We just need to find some e sub something where it belongs. And what we can say is that x is related to itself because R is an equivalence relation. And so here I actually should backtrack for a second and say at the beginning, we're going to be calling R our equivalence relation. So let's let R be the equivalence relation. Okay, so now that this is an equivalence relation, we know that x is related to x, and so that implies by definition that x is in E sub x. And so now we've found an equivalence class where x belongs. Okay, for the next part of the proof, we want to show that x is in at most one equivalence class. And so in order to do that, we'll assume that x for some element in our big set is inside two different equivalence classes. And now the goal is to show, that these two equivalence classes are equal to each other. And so these equivalence classes are sets. And so now we're trying to show a set equality. And so we can do that the way that we normally would, which is a two-part proof. We're going to want to show that E sub x is a subset of E sub y, and then also the reverse. And so here we'll let z be in E sub x. And now my goal later is to show that z is in E sub y. And now I have to connect the dots between these two lines. And so as per usual, I'll want to use the definition of what it means to be inside these sets. And I can write sort of sandwiching in between. I can write the next line after and the line above the last thing. And so in other words, I know that if z is in E sub x, that's the same as saying that z is related to x by definition. And I know then that my goal for showing that z is inside E sub y is to say that z is related to y. Okay, so now I have to somehow use the fact that z is related to x to show that z is related to y. And the one thing that I haven't used yet is this line right here, that x is in E sub y. And so let me show what that means. So since x is in E sub y, we have that x is related to y. And so now I have the two statements here, that z is related to x and x is related to y. And so the way to connect those is through transitivity. And so we know that transitivity sort of allows you to connect the dots, or in other words, when you have this chain, z to x and then x to y, you now also have the outermost relation, or in other words, z to y. And so that connects the dots that I needed here, and then I can say that that does imply that z is in E sub y. The proof that E sub y is contained in E sub x is very similar. And so I'm not going to write out all the details here, although I would encourage you to think about it just to make sure that you're following all the steps in this proof. So at this point then we have shown that that any element in our original set is in both at least one equivalence class and at most one equivalence class. So at this point, we've shown that the equivalence classes do partition the set. All right, and so now we're ready to prove the second part of this statement. And so that means that we need to show, let me highlight it here, that the elements x, y in my set are related to each other if and only if they are in the same equivalence class. And so this will also be a two-part proof. And so first, what we'll do is assume that x and y are in the same equivalence class, which I'll call E sub z. And then I want to show that x is related to y. And then just to have the rest of the proof structure down, the other thing I need to show is that if x and y are related to each other, so in other words, I'm going to assume that x is related to y, and then I'm going to want to show that x and y are both in the same equivalence class. Okay, so it turns out that both of these parts aren't going to be too difficult. So let's look at the first one, where I'm assuming that x and y are both in the same equivalence class, and then I want to show that x is related to y. And so if x and y are both in EZ, then I know that x is related to z and y is related to z. And so that's just by the definition of being in that equivalence class. And so now I need to show that x is related to y. And you could see that this almost looks like transitivity, but it's not quite right because I would need it to be x related to z and z related to y in order to use transitivity. But I can use symmetry first to flop the second relation. So by symmetry, the fact that y is related to z implies that z is related to y. And then by transitivity, the fact that x is related to z and z is related to y implies that x is related to y. And so then I've shown what I need to for that part of the proof. Okay, now we have this last line here where all we need to do is show that x and y are in the same equivalence class if x is related to y. Well, if x is related to y, then we know that x is in E sub x, which we saw above by reflexivity. And since y is related to x through symmetry, that implies that y is also in E sub x. And so then they're both in the same equivalence class, and we're done.